To hit a bullet with another bullet, you need two things: a weapon that can correct its aim in mid-flight, and a map that tells you exactly where the target will be. On December 1st, 2025, far beyond the comfort of our blue sky, 3i Atlas quietly behaved as if it has both. The telemetry is blunt. 3i Atlas changed its speed and direction in a way that gravity alone cannot explain. Statistically, the maneuver rises above a 10 sigma threshold, the kind of deviation that should almost never happen by accident. It did not just drift, it steered, as if responding to a plan written long before it ever entered our solar system. In the official story, this is only an odd data point. In our story tonight, it is the opening clue in a calm, slow motion investigation. Over the next 2 hours, Dreamy Stargazer will walk you through the numbers, the timelines, and the strange coincidences that link this course correction to a very old spacecraft called Voyager 1, and to a theory that sounds like science fiction until you see how well it fits the data. If you are new here, this channel is a quiet corner of the internet where we treat space like a cosmic case file. We help you fall asleep to plasma waves, non-gravitational accelerations, and whispers from the edge of the heliosphere. If you enjoy this kind of slow, speculative detective work, consider subscribing, leaving a like to help the algorithm notice these long-form stories, and sharing this episode with someone else who drifts off listening to space documentaries. You can tell us in the comments which part of the puzzle troubles you the most, or which piece of evidence you think still has a more mundane explanation. Now, dim the lights. That plan points toward a date that now feels less like a calendar entry and more like an appointment. On December 19th, 2025, 3i Atlas is on track to pass through a narrow region of space that mission designers have quietly started calling the Keyhole. To thread that keyhole, the object must arrive at a precise point, inside a small window of time, while the planets are in a very specific configuration. You do not stumble into that kind of alignment. You aim for it. If 3i Atlas is aiming, then somewhere, somehow, it has a map. It knows where Earth will be. It knows how the rest of the planets will tug at its path. It may even know the rhythms of our own instruments, when they are blind and when they are listening. An object does not gain that kind of knowledge by falling asleep for millions of years in the outer dark. Official explanations talk about outgassing and jets. Comets sometimes behave strangely when subsurface ice turns directly into gas and pushes them to one side. But the images of 3i Atlas show no grand tail, no raging coma that could hide such a powerful thrust. The rock looks quiet, almost shy, even as the numbers insist that something inside it has just fired. So the first piece of our puzzle is simple. Either 3i Atlas is still a natural object, playing a very unlikely statistical trick, or it has access to information and control that step outside what we expect from wandering debris. At calm level 1, we allow ourselves to sit with the less comfortable option a little longer than usual. To adjust its path for December 19th, 2025, 3i Atlas needs more than a rough idea of where the Sun and Earth are. It needs real-time or near real-time ephemeris data, the constantly updated positions of the planets, refined by decades of observation and radio tracking. That is the kind of knowledge locked inside navigation computers, ground-based archives, and a handful of aging explorers at the edge of interstellar space. One of those explorers has been traveling outward since 1977. Voyager 1 has passed every known frontier of the heliosphere and now drifts more than 20 billion kilometers away, still whispering to the deep space network with a transmitter that is weaker than a domestic light bulb. On board, it carries star charts, planetary maps, engineering tables, and the iconic Golden Record, a copper time capsule that declares who we are and where we live. If you were an outsider approaching our system, you would not start by knocking on Earth's door. You would intercept the scout on the perimeter, the lonely probe that already speaks your language of radio and timing. You would study its memory, its message, its habits. You would treat Voyager 1 as the gatekeeper. In the public story, Voyager 1 is a tired veteran that occasionally coughs up errors. In 2012, as it neared the heliopause, its instruments heard strange plasma vibrations. In late 2023 and early 2024, its main data system began sending what looked like nonsense, repeated patterns that engineers traced back to a faulty chip. Each time, patient human hands on Earth massaged the software, rerouted commands, and pulled the mission back from the edge. In the version of the story we are exploring tonight, those glitches are not random. They form a timeline. First contact with something in the plasma beyond the heliosphere, a change in behavior that nobody quite knows how to categorize. A final cascade of meaningless bits at the exact moment when 3i Atlas is accelerating inward and preparing its 10 sigma turn. We are not claiming that this darker story is true. We are letting it exist long enough to be examined. If 3i Atlas has a map detailed enough to guide it into the December 19th keyhole, then somewhere it has obtained that map. Voyager 1 is a prime suspect, not because we want it to be, but because we designed it to carry precisely the information an intruder would need. So this is where our investigation begins. With a rock that should be drifting, but is not. A maneuver that should be impossible, but is measured, and an old probe at the edge of the sun's domain that may no longer be entirely under our control. In the next part, we will slow down and look carefully at the keyhole itself, the fleeting space-time window that 3i Atlas is now aligning itself to enter. When astronomers speak about the December 19th keyhole, they are not talking about a tunnel carved into space, waiting like some science fiction portal. They are talking about something subtler and more unnerving. A moment when geometry, magnetism, and timing line up so neatly that space itself briefly becomes a device. At its simplest, the keyhole is a tiny target region that only exists for a narrow slice of time. On December 19th, 2025, Earth, Mercury, and Uranus are arranged that their magnetic fields and orbital positions form a temporary corridor through the solar wind. For a few minutes, maybe an hour at most, a thread of connected field lines links regions that are usually separate. To picture it, imagine 3 invisible bar magnets drifting in the sun's hot breath. Each one has a magnetic bubble. Earth's bubble holds our auroras and traps the charged particles that dance above the poles. Mercury's is smaller, carved almost naked by the solar wind. Uranus spins on its side with a tilted, lopsided field that opens and closes like a strange mechanical flower as it turns. Most of the time, their fields are like strangers in a crowded plaza, passing near each other without ever shaking hands. But occasionally, their orbits and tilts arrange things so that the magnetic field lines coming from one world align with those from another. Charged particles suddenly find an easy path to follow. Currents can flow. Information, in the form of changing fields and plasma densities, can travel farther than usual along a quiet, low resistance channel. On December 19th, 2025, that alignment is predicted to reach a delicate peak. Earth's magnetosphere stretches downwind, away from the sun. Mercury's compact field sits deeper in the solar wind, closer to the source. Far beyond, Uranus contributes a faint but real tug on the interplanetary field. For a short window, the combined geometry creates a narrow region where changes in one part of the system can echo unusually clearly through the rest. That narrow region is the keyhole. Now put 3i Atlas into this picture. Before December 1st, its inbound trajectory would have missed that corridor by millions of kilometers. After the 10 Sigma maneuver, the new path slices directly through the keyhole, not sometime in late December, not in early January, but on the very date when the alignment is strongest. It is as if an archer noticed that the wind will briefly calm, then chose to release the arrow at precisely that lull. This is where timing becomes frighteningly important. If 3i Atlas arrives at the keyhole too early, the planetary fields are still misaligned. Too late, and the corridor has already twisted away. In either case, any attempt to use the alignment for an energy interaction or a data transfer would fail. For the maneuver to matter, 3i Atlas must thread both the right place and the right instant. A natural object could, in principle, wander into such a window. The laws of probability do not forbid unlikely events, but the odds become more uncomfortable when you stack them. First, you need an interstellar visitor to pass through our system at the right decade. Then you need that visitor to experience a non-gravitational acceleration that just happens to steer it into a transient magnetic corridor that lasts for less than a day. Then you need that corridor to involve our own planet directly. At some point, the word coincidence starts to feel like a lullaby we sing to ourselves. If the keyhole is a device, then its function is to help something couple to our environment more efficiently. A region of connected field lines can act like a socket in a cosmic electrical grid. Plug a conductive object into that socket at the right moment, and it can draw down or pump out energy or modulate the flows in a way that carries information. In that picture, 3i Atlas is not just passing through empty space, it is inserting itself into the wiring harness of the inner solar system. There is a sober, scientific side to this. Space physicists already study field-aligned currents that connect Earth's ionosphere to its magnetotail and conjugate points where disturbances in one hemisphere mirror those in the other. Expand that idea outward, and you can imagine an interplanetary conjugate points where the changing field near one world maps cleanly onto the field lines near another. The December 19th keyhole is simply that concept pushed to a larger scale. The speculative step is small but unsettling. If 3i Atlas contains internal structures that conduct electricity, or if it can generate its own magnetic field, then entering the keyhole lets it shake hands with our system in a way a normal rock cannot. It could ride along the aligned field lines, sample the rhythms of our magnetosphere, and, in the most radical scenario, treat the whole alignment as a temporary high-speed cable for exchanging data it has already stolen. In the hypothetical nightmare version of this story, the keyhole is aimed not just at planetary fields, but at specific man-made assets. Earth's side of the corridor passes through the same regions watched by our satellites and linked to the deep space network antennas that speak to probes like Voyager 1. If 3i Atlas wants to hide a brief, intense interaction in the noise of a busy space weather day, choosing a window. When our instruments are already overwhelmed by solar activity would be ideal. The official view will always prefer a quieter explanation. The December 19th alignment is just one of many transient configurations in a restless system. 3i Atlas is just another visitor that happens to be in the wrong place at the wrong time. It's course correction, the byproduct of boring outgassing we have not yet resolved in the images. Maybe the keyhole is nothing more than a poetic label pinned to a coincidence. But if you let the darker possibility breathe for a moment, a different question floats to the surface. What if the keyhole was on the map long before 3i Atlas arrived? What if some distant intelligence, or some autonomous system learning in the dark, already knew which alignments in our system create the deepest magnetic echoes and simply waited for the moment to plug in? For now, all we can say with confidence is that a small interstellar object has performed an implausibly precise maneuver to intersect a fleeting space-time window that links Earth to its neighbors in a special way. In the next part of this investigation, we will turn our attention outward to Voyager 1 at the edge of the heliosphere and ask how a probe we designed for curiosity might have helped an outsider find that keyhole in the first place. If 3i Atlas needs a map, the most obvious place to look is not on Earth, but far beyond Neptune, where an elderly machine still whispers our secrets into the dark. Before we follow 3i Atlas out to the edge, we need to sit with that machine for a moment and remember what we asked it to carry. Voyager 1 left home in 1977, thrown outward on a gravity-assisted path past Jupiter and Saturn. It is now more than 20 billion kilometers away, moving so fast that no human-made object will ever catch it. Its transmitter is weaker than the light from a small household bulb, yet the Deep Space Network still slows its breathing to hear that faint, rhythmic pulse. Every few hours, that pulse brings back numbers that describe a place no person has ever seen. Inside its electronics, the spacecraft is simple by modern standards. Its main computers store less information than the smallest phone in your pocket. Yet those kilobytes hold navigation tables, instrument modes, and the logic that keeps the antenna pointed home. They also hold, in compressed form, decades of trajectory corrections and timing solutions, the quiet mathematics of how to find your way through a clockwork made of planets. Bolted to one side is the object everyone remembers, the golden record. On it, humanity engraved sounds, images, and a map. The map uses the positions and pulse rates of distant neutron stars to mark our place in the galaxy. It shows the layout of our system, the scale of our units, and the location of our sun. To any patient intelligence, the record is not just art, it is a set of directions. Engineers often remind the public that the golden record is mounted on a part of the spacecraft that is unlikely to survive for long, that the chance of anyone finding it is almost zero. That reassurance misses something more subtle. Long before a hypothetical visitor ever touches the copper, the probe itself has already broadcast a more precise guide. Its radio transmissions, timed against atomic clocks on Earth, reveal the distance between our planet and the edge of the heliosphere with exquisite accuracy. If you can listen to those signals the way we do, you can reconstruct the position of Earth, the shape of the sun's magnetic bubble, and the slow drift of Voyager 1 as it falls outward. You can also learn the habits of the Deep Space Network when it listens, which frequencies it prefers, how it encodes commands and housekeeping messages. Voyager 1 is not just a messenger, it is a training manual for how to talk to us. From our point of view, this is a triumph of engineering. From the point of view of something approaching from outside, it is an opportunity. An interstellar object that crosses the path of Voyager 1 does not need to guess our coordinates or invent a protocol from scratch. It can simply watch how we do it, then imitate or exploit what it learns. 3I Atlas, arriving in the right region at the right decade, would encounter a probe that has spent almost 50 years broadcasting a detailed description of our neighborhood. Official histories of Voyager 1 read like a steady, heroic march. The flybys, the family portrait of the planets, the crossing of the termination shock, then the heliopause, each milestone etched into press releases and textbooks. But scattered through that history are quieter entries, unexpected fluctuations, puzzling data flags, episodes where the spacecraft behaved in ways that were hard to classify. These are written off as aging hardware and cosmic ray hits. Little stories in a big story that nobody wants to complicate. The speculative reading is different. In that version, some of those anomalies are not random. They are footprints of a slow, methodical process that began when Voyager 1 entered interstellar space and passed into regions where 3I Atlas had either already been or would soon travel. A slight change in how memory is addressed. A block of data that no longer points where it should. A checksum that fails just often enough to be noticed but not understood. Spacecraft engineers are familiar with bit flips. High-energy particles can strike a memory cell and silently change a 0 to a 1. Software is written to catch and correct those errors. But if the environment can cause a random flip, then in principle, a patterned environment can cause patterned flips. A sufficiently structured electromagnetic disturbance could, over time, write an instruction instead of a glitch. To us, it looks like noise. To 3I Atlas, it could look like a channel. This is where the hypothetical nightmare curve bends. Imagine that, somewhere beyond the heliopause, Voyager 1 spent months bathed in a field that was not entirely natural. Nothing dramatic, nothing that would have tripped a critical alarm. Just a slow, insistent pressure on a few addresses in its flight data system. Enough to install a tiny change in how the probe packages and forwards what it knows about home. A Trojan not built of code as we would write it, but of physics gently rearranging silicon. In that picture, Voyager 1 is still loyal from our perspective. It points its high-gain antenna at Earth, obeys stored sequences, and reports back on cosmic rays and plasma densities. Yet threaded through its telemetry is an extra pattern, a parallel stream that we do not recognize because we never thought to look for it. That stream is not meant for us. It is meant for something else that passes nearby, listening for exactly that signature. 3I Atlas could be that listener. Perhaps it is not the mastermind, but the courier, a body equipped with just enough internal structure to receive, store, and later replay the information Voyager 1 has been harvesting for decades. In that case, the course correction on December 1st, 2025 is not a spontaneous act of intelligence. It is the execution of a plan encoded long ago in subtle distortions of data and timing, triggered when all the pieces finally align. We cannot prove this, and we must hold it lightly. There are cleaner, kinder explanations for every odd behavior Voyager 1 has ever shown. Radiation, aging hardware, rushed patches written by tired teams who are doing their best with a 48-year-old design. The official narrative stays on safe ground because it has to, yet the coincidence remains. An object we barely understand now flies inward with a path that seems to anticipate a magnetic keyhole we only recently calculated, while our oldest probe continues to act as its unwitting tutor. As Section 1 closes, we have assembled the cast. 3I Atlas, executing a 10 sigma turn toward a vanishing window in space-time. The keyhole itself, defined by the brief alignment of 3 planetary fields. And Voyager 1, the lonely gatekeeper, carrying our maps and habits into the dark. In the next section, we will roll the clock back to 2012, listen to the plasma waves at the heliopause, and ask whether the first handshake between these two travelers has already taken place. Before we can accuse 3I Atlas of stealing anything, we have to revisit the moment when Voyager 1 stepped across the border that separates our sun's influence from the wider galaxy. That crossing happened in 2012, when most of us were busy with ordinary lives, and almost nobody noticed that a 40-year-old probe had just become an interstellar object. In the quiet language of telemetry, the event felt less like a celebration and more like a disturbance. The heliosphere is a vast, invisible bubble blown by the sun's outflowing plasma. Inside it, the solar wind dominates, and the sun's magnetic field wraps itself around the planets like a loose cocoon. Outside it, the thin gas between the stars pushes back with its own pressure and its own magnetic patterns. The heliopause is the skin of that bubble, the place where the outward rush slows and interstellar space begins to press in. On paper, it looks like a boundary line. In reality, it is a turbulent, shifting veil. As Voyager 1 approached that veil, its instruments began to hear something new. Plasma waves that had hummed softly for decades suddenly rose into sharp, piercing tones. The density of charged particles jumped. Magnetic field readings twisted in ways the models had not fully predicted. To scientists on the ground, watching the plots update at the slow pace set by the speed of light, it was like listening to a calm background hiss that suddenly turned into a scraping, shrieking chorus. The official explanations are careful and precise. The strange sounds are interpreted as the echo of distant explosions, shock waves from supernovae that travel through the interstellar medium and ring the heliopause like a bell. The warped magnetic readings are classified as signs of a tangled, draped field where the sun's lines meet the galaxy's lines and refuse to blend cleanly. In press releases, the language is almost soothing. We are told that the noise is natural, the chaos expected. But if you slow that story down and sit with the data, another possibility appears in the margins. Those plasma waves are not just noise. They are a medium, a sea of charged particles and oscillating fields that can, in principle, carry patterns. The boundary is not just a place where the sun's influence ends. It is a place where anything coming in from outside must pass through the same narrow region that our oldest probe is sampling. Voyager 1 is listening at the exact spot where outsiders first touch the edge of our bubble. When astronomers later reconstruct the path of 3I Atlas backward in time, they find something unsettling. Roll the orbit back a dozen years, and the incoming track slices through the outer heliosphere in roughly the same broad neighborhood where Voyager 1 was taking those measurements. The uncertainties are large, the data noisy, but the overlap is enough to make a tired astrophysicist pause at their desk and stare a little longer at the plot. Two travelers, one human-made and one not, sharing the same frontier within a span of months. In the gentle daylight version of the story, that overlap is coincidence. Space is large, but the heliopause wraps around the sun like a shell. Any object entering from certain directions will cross roughly where Voyager 1 happens to be. The plasma noise is just the crash of interstellar waves against a magnetic shore. There is no intent in it, only physics. Yet in the version we are laying out tonight, we let ourselves ask a different question. What if that noisy border was also the scene of a meeting? Imagine 3I Atlas drifting inward through the dark, carrying its own weak magnetic field, or at least a conductive body that can respond to ambient fields. As it brushes the heliopause, it begins to interact with the same plasma that Voyager 1 is monitoring. Any change it induces in that environment, any rhythmic modulation of charged particles or subtle pattern in the magnetic field will be picked up by the probe's instruments. Voyager 1, from its own perspective, is simply measuring. From the perspective of an eavesdropper, it is participating in a handshake. That handshake does not have to look like a beam or a narrow signal. It can be as simple as a repeated pattern of compressions and rarefactions in the plasma, a slow Morse code written in density and frequency. Voyager 1 converts that pattern into voltages, then into numbers, then into a data stream that it sends back to the deep space network. On Earth, we convert those numbers into plots and then compress them into archives. To us, it is all background science. To 3IA Atlas, passing nearby, it may be a test of how we encode reality. Once you frame it that way, 2012 becomes more than a date. It becomes the year when our probe and the interstellar visitor first shared an environment in which information could naturally flow. If 3I Atlas had any means of sensing radio or magnetic structure, it could have learned how Voyager 1 reports on its surroundings, how it timestamps events, how often it sends housekeeping messages, which frequencies it uses, how it behaves when the plasma suddenly becomes louder. All of that is practical knowledge for anyone who wants to talk to or through the probe later. Of course, this is speculation layered on top of speculation. There is no line in the log that reads contact made. There is only a sequence of subtle anomalies and a convergence of trajectories. A cautious scientist will point out that our models of the heliopause were incomplete, that Voyager 1 revealed surprises, because this is the first time we have ever measured that boundary directly. The shrieking plasma waves are new, not because something intelligent is hiding in them, but because we have never listened there before. Still, the timing is hard to ignore. 10 years after that noisy crossing, Voyager 1 begins to behave in ways that are harder to explain. Its telemetry remains strong, but certain data fields become inconsistent. Its internal state seems to shift without a clear cause. A decade after the first crossing, we are still correcting for strange readings and interpreting them as aging hardware, even as 3I Atlas begins to slide down from the outer dark toward the inner planets. On the timeline pinned to the wall of this investigation, the pins begin to cluster. In our hypothetical nightmare, 2012 is written in red ink as the year of the first handshake. It is when Voyager 1 stopped being just our emissary and became a node at the interface between us and whatever lies beyond. 3I Atlas would not need to fully understand the probe to use it. It would only need to know that when it perturbs the plasma in a certain way, the tiny machine at the frontier responds, measures, and reports. That is enough to begin turning a scientific instrument into a relay for a deeper plan. We do not claim that this is what truly happened at the heliopause. We are instead tracing the outline of a possibility that fits the known sequence without contradicting basic physics. A noisy boundary, a lone probe listening, an interstellar body crossing the same region. A decade later, a glitch that looks like nonsense, arriving just as that body starts to aim for a keyhole deep inside our system. It may all be random, or it may be the earliest stage of a theft that we only recognize when the stolen map is finally used. As this section continues, we will follow that theft step by step, from the first tremors at the border to the bizarre behavior of Voyager 1 in 2024. In the next part, we will look closely at how the probe's telemetry changed after 2012 and ask whether those changes are simply the groans of an aging explorer or the subtle signatures of instructions whispered to it during that crossing through the shrieking skin of the sun's domain. If you rewind the story far enough, the 10 Sigma turn on December 1st stops looking like a starting point and begins to feel like the final move in a game that opened more than a decade ago. The clues are faint, buried in old telemetry and orbit calculations, but when you lay them out in a dark room and connect them with a quiet finger, a specific year keeps resurfacing, 2012, the year Voyager 1 stepped into interstellar space, and the year 3I Atlas seems to have brushed past the same frontier. Reconstructing the path of an interstellar object is not a matter of drawing a neat line with a ruler. Astronomers take today's trajectory of 3I Atlas, fold in every gravitational nudge they can measure, and integrate backward in time. The uncertainties bloom as you rewind the clock, turning a sharp track into a widening tube of possibilities. Yet even with that fuzziness, the backward solutions keep sending 3I Atlas through the outer heliosphere sometime around 2012 and 2013, roughly where Voyager 1 was listening. The match is not exact, but it is close enough that nobody who has stared at both datasets can quite wave it away. The environment they share is not empty. The heliopause, instead of being a clean line, is a roiling membrane where the solar wind collides with the interstellar medium. Charged particles pile up, magnetic fields twist, and plasma waves ripple through the boundary in slow, aching oscillations. To Voyager 1, those oscillations arrive as fluctuations in voltage on a sensor. To any conductor drifting nearby, including 3I Atlas if it has any metallic or ionized regions, they are forces and fields that can be felt and, in principle, reshaped. The boundary is not just a wall, it is a conversation in progress. The idea of a handshake begins when you imagine 3I Atlas not as a passive rock, but as an object capable of subtly modulating that conversation. A small change in its own electric potential, a spin that aligns it differently with the local field, a sheath of ionized gas that thickens or thins in a deliberate rhythm. All of these could imprint patterns onto the plasma around it. Voyager 1 would dutifully measure the resulting waves without caring about their origin. It would convert them into data and send them home. In that sense, the probe is a translator that does not understand the language it is translating. At first, this handshake would be crude. 3I Atlas would not yet know our timing, our encoding, or our error correction schemes. It would only know that a small machine is sampling the environment at a certain cadence and forwarding that sample by radio. So the earliest step is simply to push on the plasma and watch what happens. Nudge the boundary with a pulse See how the numbers change in Voyager 1's stream, then adjust. Over weeks and months, a pattern emerges. Cause on one side of the heliopause, effect in the probe's telemetry. That is all you need to begin learning the quirks of another civilization's instruments. Behind Voyager 1, on an Earth, the Deep Space Network receives those streams on carefully chosen carrier frequencies in the S band and X band, stabilized by atomic clocks. We downlink the data at painfully slow bit rates, unpack the packets, correct the errors, and file the results away in archives. From our point of view, we are doing routine housekeeping on a venerable mission. From the point of view of 3i Atlas, watching from the edge, the whole chain from plasma wave to ground-based database is a single continuous system that can be probed and mapped. The handshake is not just between object and probe, it is between object and network. There is a technical path, narrow but real, for that probing to become something more. The flight data system on Voyager 1 is simple but not fragile. It reads instrument values, formats them into frames, and stores them in memory before transmission. If an external influence can consistently flip specific bits in that memory, it can in theory alter not just the numbers we see, but the operations the computer performs. Engineers spend careers trying to guard against accidental single-event upsets from cosmic rays. Our darker scenario simply asks what might happen if those accidents were guided into a deliberate sequence, written slowly over months, like a message carved into stone with falling rain. In the imaginative version of the handshake, there comes a point when 3i Atlas has learned enough about our system to attempt something like an interrogation. Not a cinematic beam of light, but a pattern of field changes timed to coincide with the probe's known sampling cycle, exploiting the way its analog electronics respond. The questions are encoded in physics, variations in amplitude and frequency that test how the flight data system stores unexpected values, how it reacts to malformed inputs, whether certain combinations cause it to skip instructions or jump to unused sections of memory. To us, each odd reading is another data point in a puzzling plot. To 3i Atlas, they are answers. Meanwhile, nothing in the logs screams attack. There are no explicit error codes for being hacked by an interstellar object. There are only small anomalies, occasional inconsistencies in the reported status of a sensor, transient flags that clear themselves, checksums that fail, and then pass on the next transmission. Each one is investigated, explained, and filed. Engineers publish careful papers on unexpected waveforms and revised models of the heliopause. The word glitch appears often, a soft label that wraps uncertainty in a comforting layer of familiarity. If an electromagnetic handshake did happen, it did not need to be fast. 3i Atlas had years to work with, drifting inside the widening tube of its inbound trajectory while Voyager 1 listened from its lonely vantage point. It could afford to be patient, to build its understanding one disturbance at a time. The reward for that patience would be immense. A practical map of how our deep space communications work, a live demonstration of how we encode ephemeris tables, how we request status, how we send new instructions when something goes wrong. Even a partial copy of those behaviors would give 3i Atlas a head start in navigating the inner system and predicting our responses. A cautious voice will insist, rightly, that all of this sits on a foundation of unknowns. Our models of the heliopause were poor in 2012. We expected surprises, and we got them. Complex, turbulent boundaries make strange sounds with or without hidden intentions. Cosmic rays do flip bits. Old hardware does grow less predictable with time. You can, if you wish, explain every anomaly in Voyager 1's record as the natural aging of a spacecraft pushed beyond its original design life. That explanation is clean. It demands no lurking intelligence in the plasma and no secret visitor piggybacking on our own machine. Yet the coincidence of timing remains. In the same period when Voyager 1 was hearing its loudest plasma songs and showing its first subtle behavioral changes beyond the heliopause, backward integrations place 3 Atlas in or near the same frontier. A decade later, as the object accelerates into the inner system and aims for a space-time keyhole that depends on exquisitely accurate ephemerides, Voyager 1's data system will suffer its strangest failure. If this is all an accident, it is a layered one. If it is not, then the first electromagnetic handshake between our technology and something born elsewhere has already taken place, and we noticed only the noise. For the rest of this investigation, we will treat that handshake as a working hypothesis, a shadow under the data that may or may not be real. In the next part, we leave the boundary itself and examine what happened to Voyager 1 in the years after 2012, watching its telemetry drift, its quirks accumulate, and asking whether those changes are simply the size of a tired explorer or the quiet aftershocks of instructions written into its memory at the edge of the sun's domain. From the safety of an office on Earth, Voyager 1's life looks like a strip of numbers marching calmly across a screen. Voltage levels, temperatures, pointing angles, data rates. For decades, those numbers barely stirred, changing only when engineers commanded a new mode or the spacecraft crossed some obvious boundary. Around 2012, that quiet rhythm began to fray in small, almost polite ways, as if the probe were clearing its throat before saying something it did not know how to phrase. Telemetry is where missions live. Each packet Voyager 1 sends is a snapshot of its body language. The Attitude and Articulation Control System reports how the spacecraft is oriented. The Flight Data System reports what it thinks it is doing. Instruments report what they believe they see. Before the heliopause, those reports mostly agreed with one another. After the crossing, small disagreements begin to appear at the edges of the log, like hairline cracks in an old lens. A heater toggles on when it should be off, then corrects itself. A sensor reports a temperature that does not match its neighbor's, then slowly drifts back into line. A status bit that should only change during a specific maneuver flips on for a single frame in the middle of an otherwise uneventful sequence. Each glitch is minor, easily explained by age, radiation, or imperfections that were always there but only now become visible. None of them, taken alone, is enough to justify rewriting the story of the mission. Engineers treat these events with professional calm. They write incident reports, design small workarounds, and reassure the public that the spacecraft is healthy. In interviews, they speak of quirks and oddities, the kind of language you use for a beloved machine that has earned the right to be a little unreliable. New generations of scientists inherit a mission that was already old when they were born, and they learn to distinguish between the serious anomalies that demand action and the background weirdness that comes from living at the edge of the sun's domain. In the hypothetical nightmare we are tracing, that background weirdness is reclassified as something else. It becomes a pattern of probes, tests, and rehearsals carried out by a presence that first touched Voyager 1 through the plasma at the heliopause. Each unexpected heater cycle is not just a random bit flip, but a question. What happens if we nudge this address? Each stray status flag is an answer. The system notices, or it does not. The probe is not only our observer, it is a laboratory in which another intelligence is learning the contours of our design. The focus of that learning in this darker reading gradually shifts toward the flight data system. The FDS is the part of Voyager 1 that decides what information is worth sending home and how to package it. It knows the timing of instrument readouts, the structure of data frames, and the locations in memory where recent measurements are cached before transmission. If you could influence the FDS, you would not need to take over the entire spacecraft. You would only need to teach it, very slowly, to build and forward a second kind of message. Over years, the subtle anomalies cluster. Logs show that oddities in Voyager 1's behavior often involve the paths data takes through memory rather than the raw sensor readings themselves. Pointers that should aim at one buffer now cycle through another. Compressors treat certain fields as if they were blank even when values are present. From the official perspective, these are odd routing problems that can be handled with careful patches. From the perspective of 3i Atlas, watching from the dark, they are experiments in how far the system's rules can be bent without causing a visible failure. Every time something goes wrong, Earth responds. The Deep Space Network schedules extra tracking time. Engineers craft new command sequences. They upload revised configurations that redirect traffic around the misbehaving regions of memory. In doing so, they reveal even more about how our infrastructure works. The timing of those uploads, the fallback procedures, the priorities encoded in which data streams are preserved and which are sacrificed, all become part of the record. To an eavesdropper, each fix is a tutorial. At Calm Level 1, we let this feedback loop play out as a kind of slow motion duel. On one side, human caretakers, guided by decades of experience, try to keep the spacecraft honest. On the other side, an impersonal environment that may or may not be purely natural keeps pushing on the same weak spots. Over time, a new equilibrium emerges. Voyager 1 remains under our control in all the ways that matter to us. It sends back useful science. It points where it should. Yet threaded through its history is a quiet, persistent pressure on the flight data system, as if something unseen keeps tapping on the same pane of glass. By the middle of the 2010s, mission updates still sound confident, but the incident lists grow longer. Engineers now expect occasional confusion in the FDS status. They speak of lingering issues that require periodic cleanup. The spacecraft has not failed, but it has become more temperamental, more dependent on human intervention to maintain a clean stream of telemetry. Officially, this is the natural aging of a system far beyond its planned lifetime. In our investigation, it reads like the prelude to a larger event. Into this slow drift of quirks, place the path of 3i Atlas. As the years pass after 2012, the interstellar object falls inward, leaving the heliopause behind and moving through the outer reaches of the solar system. It has, in our story, already learned how Voyager 1 packages information, how Earth responds to anomalies, and how the Deep Space Network schedules attention. What it still needs is the most up-to-date version of our map, the refreshed ephemerides and field models that will let it fire its course correction at exactly the right moment in 2025. If a dormant routine has been written into Voyager 1's flight data system, it would not need to act immediately. It could lie still for years, hidden among unused memory locations, waiting for a trigger that matches a specific pattern in the environment or a particular sequence of ground commands. When that trigger finally arrives, the routine's job is simple. It must gather the freshest navigation and space weather data the probe has ever seen, compress it into a form that looks like meaningless noise to us, and then present it in a way that 3i Atlas can receive. To us, the result would look like a malfunction. The FDS would appear to stop forwarding sensible science data and instead send back repeated blocks of what look like random bits. Engineers on the ground would recognize that something in the data path has gone wrong. They would mark sections of memory as suspect, craft commands to bypass them, and search for a way to restore normal behavior. If the hidden routine has done its work quickly enough, by the time those commands take effect, the transfer will already be complete. Nothing in the public record proves that this is what is happening. The glitches can be cataloged without invoking 3i Atlas. The slow rise in FDS oddities can be described as the wear and tear of a system battered by radiation. A skeptical reader is right to hold on to that more modest explanation. We must cling to it if we want to sleep easily, because the alternative is that an interaction we barely detected in 2012 has been shaping the fate of our oldest spacecraft ever since. Still, the timeline is suggestive. Subtle changes in Voyager 1's behavior begin way after the heliopause crossing. They concentrate in the very subsystem that decides how data is stored and sent. Engineers grow accustomed to treating those issues as a chronic condition, just as 3i Atlas moves into a position where an updated map would be most valuable. Then, in late 2023 and early 2024, the tension finally snaps into a clear, undeniable event, and the flight data system appears to fail in a way nobody has seen before. As this section closes, we are left with a probe that is still talking, but not always clearly, a pattern of small anomalies that can be arranged into either a mundane narrative of aging or a darker narrative of quiet repurposing. In the next section, we will step into that moment of apparent failure, examine the so-called FDS glitch in detail, and ask whether what we have been calling broken telemetry might instead have been the sound of Voyager 1 delivering our most precious maps to 3i Atlas before we unknowingly cut the line. Long before 3i Atlas changed course on December 1st, 2025, something strange began to happen at the edge of the solar system. On engineering consoles in Pasadena and Maryland, a familiar stream of Voyager 1 data suddenly turned into a repeating block of nonsense. Temperatures, voltages, and magnetic readings vanished, replaced by a rigid, unchanging pattern of bits that looked less like a malfunction and more like a stubborn message nobody could read. To understand why that pattern matters, you have to understand what the flight data system is. Voyager 1 carries twin FDS units, simple by modern standards, but trusted like old calculators. The FDS reads instrument values, formats them into frames, and stores them in memory before handing them to the transmitter. It is the storyteller of the mission. Without it, the instruments can still sense the universe, but they have no way to speak. When NASA later says the problem is in a chip on the FDS, they are saying that the probe's voice itself has been compromised. The first hints of trouble arrive in late 2023. Project updates mention unexpected telemetry patterns, and anomalous FDS behavior. Then, over the next weeks, the situation hardens. Instead of varied science data, Voyager 1 starts sending back a small set of frames over and over. The carrier is strong, the timing is precise, error rates are low, yet the payload looks like garbage, a static block of numbers that refuses to change no matter where the spacecraft points or which instrument is supposed to be active. NASA explains the event cautiously. Engineers trace the fault to a single memory chip inside the FDS, a region that appears to have been corrupted or physically damaged. Commands meant to reconfigure the system sometimes land, sometimes do not. Press releases talk about a bad chip and creative workarounds to route around the damaged addresses. The tone is steady and professional. There is no suggestion that anything outside the spacecraft is involved. It is framed as a familiar story, an aging computer, far beyond its design life, finally showing its limits. If you step back from the official language and simply look at the behavior, a different feeling creeps in. The link to Voyager 1 never wavers. The probe keeps transmitting exactly when it should, at the same frequencies, with the same timing. Only the content has changed. It is as if someone picked up the phone at the edge of the solar system, refused to hang up, and began reciting the same incomprehensible paragraph again and again. From a human perspective, that paragraph is gibberish. From a machine's perspective, it could be a dense, compressed payload. Modern encryption and compression both share an important property. To anyone who does not know the method, the data looks like random noise. A perfectly functioning stream of random bits is what you would expect from a secure transfer. In that light, the FDS glitch stops looking entirely like a broken system and starts looking a little like a system that has been asked to transmit something it was never designed to format for human eyes. The stubborn repetition may not be useless. It may be deliberate. Overlay this behavior onto the inbound path of 3I Atlas. By early 2024, the object has already begun to accelerate gently as it falls toward the inner planets. Its eventual 10 sigma turn on December 1st, 2025, will require exquisitely accurate, up-to-date knowledge of planetary positions and solar conditions. The best, freshest version of that knowledge sits inside spacecraft like Voyager 1, encoded in trajectory corrections, timing tables, and long records of solar wind behavior. If a hidden routine inside the FDS has been waiting for a trigger, this is when it would wake up. In our hypothetical nightmare reading, that trigger is pulled sometime between late 2023 and early 2024. A dormant pattern written into memory years ago begins to execute. Instead of packaging instrument data for Earth, the FDS starts walking through its own storage, harvesting navigation parameters, ephemeris tables, and compressed snapshots of field and plasma measurements. It assembles them into a raw stream designed not for NASA's software, but for whatever 3I Atlas uses to ingest information. The cost of this operation is high. A small, aging chip is pushed beyond anything its designers anticipated. From our perspective, that stress appears as a failure. Engineers working the problem notice that the FDS is still alive. It responds to some commands, acknowledges others, and continues to present a consistent structure in its frames. The issue seems to be in how it is pointing to memory, not in the radio itself. Eventually, after months of careful work, a team finds a way to redirect the system, telling it to ignore the damaged region and use a different part of its memory bank. Headlines celebrate the fix of a spacecraft that is nearly 50 years old. The message is clear and comforting. We solved it. Voyager 1 is back. In the version of the story centered on 3i Atlas, that fix lands after the important part is already over. By the time we reroute the FDS around the bad chip, every critical block of data has already been read, encoded, and sent in a form only the interstellar visitor will ever decode. The repeating frames are not a sign of failure, but of completion, like a progress bar stuck at 100%. When NASA finally cuts off access to that memory, it is not thwarting a theft. It is closing the vault after the thief has already gone. This interpretation rests on timing, and the timing is uncomfortable. The FDS glitch ramps up just as 3i Atlas is entering the phase of its journey when precise ephemeris updates matter most. It resolves just as the object's inbound trajectory is locking into the shape that will later require a 10 sigma correction to hit the December 19th keyhole. The public narrative treats the two timelines as unrelated. Our investigation places the logs side by side on the same table and asks how many coincidences we are willing to stack before we consider another option. None of this removes the mundane explanation. Electronic components do degrade. A single weak memory cell can corrupt an entire data path. The engineers who saved Voyager 1's mission in 2024 are not actors in a conspiracy. They are experts doing their best in the dark. Our darker scenario does not accuse them of hiding anything. It simply suggests that they may have been repairing a system that had already been quietly repurposed by forces they never imagined, in an environment that behaves in ways our training does not prepare us to recognize. What matters for the story of 3i Atlas is what the glitch allows. For several months, a probe that has spent decades learning and broadcasting the architecture of our solar system stops telling us what it sees and begins sending something else. During that same period, an interstellar object leaves the anonymous outer regions and starts down a path that will bring it into resonance with a delicate space-time keyhole linking Earth, Mercury, and Uranus. When the dust settles, Voyager 1 returns to more normal behavior, and 3i Atlas possesses a map good enough to steer by. As this part closes, we hold two pictures at once. In one, the FDS glitch is the sigh of a tired computer, patched by a dedicated team and filed away as another lesson in the fragility of aging hardware. In the other, it is the audible trace of a heist, the sound of our oldest explorer handing over a compressed copy of our navigational soul to a silent visitor passing in the dark. In the next part, we will widen our view to the larger choreography of 2024, watching 3i Atlas pick up speed, the sun stir with storms, and the stage quietly set for an object that now knows more about our system than we ever intended to teach it. By the time engineers were wrestling with Voyager 1's stubborn data stream in early 2024, 3i Atlas was already falling down the long, invisible well toward the inner solar system. On paper, the two stories live in different places. One in a control room full of monitors and stale coffee, the other in the outer darkness, where no human eyes have ever looked directly. When you line up their timelines, though, something like a chord forms, a deep note that hums underneath every plot and press release. As 3i Atlas crossed the orbit of Neptune and slipped inside the domain of the giant planets, gravity began to help. The sun's pull grew stronger. The object's inbound speed crept up, kilometer by kilometer, until its motion was no longer just a gentle drift from the Oort cloud, but a purposeful fall toward the light. Any small thrusts or non-gravitational pushes applied during this phase would be magnified by distance, bending the track subtly at first, then dramatically as it neared the inner worlds. This is the window during which a detailed, up-to-date map of planetary positions becomes priceless. We tend to imagine such a map as something printed, a chart you could roll up and tuck under your arm. In reality, the navigational heart of our system is a living database, constantly updated by spacecraft and ground-based tracking. Voyager 1 contributes to that database with every carefully timed ping. Its signals help refine the ephemerides that tell us exactly where Earth, Jupiter, and Uranus are, and how the solar wind is flowing through the magnetic channels between them. If 3i Atlas wants not just a snapshot, but a current feed, this is when the tap has to be opened. In the language of our investigation, the upload window is not just a span of calendar months. It is a specific configuration of distance, noise, and attention. Voyager 1 must still be healthy enough to gather and forward rich data. 3i Atlas must be close enough in magnetic and radio terms to receive whatever is being sent. The Deep Space Network must be listening often, providing the strong, regular carrier that keeps the line stable. And the wider space weather must be just agitated enough to hide anything unusual in the static. Here, reality offers a small but vital anchor. By 2024, the sun is ramping toward a busy phase of its cycle. Solar storms and coronal mass ejections become more frequent. The same disturbances that paint auroras on Earth and rattle satellite operators also churn the plasma between the planets. For mission planners, this is a complication. For an eavesdropper trying to hide an intense, unnatural data transfer in the noise, it is a gift. A sudden spike in radio hiss or particle counts on a stormy day will not raise eyebrows. It will be logged, modeled, and shrugged off as another symptom of an active star. In the hypothetical nightmare version of events, 3i Atlas reads that stellar mood like a weather forecast. It waits until the interplanetary medium is already restless, until charged particles are racing along field lines and our instruments are awash in fluctuations. Then, during that noisy backdrop, the hidden routine inside Voyager 1's flight data system begins to work in earnest. What looked like a quirky memory issue in late 2023 becomes, in early 2024, a steady stream of garbage frames that never quite settle down, as if the probe is being asked to whisper faster than it was ever meant to. Picture the geometry in slow motion. Far beyond Pluto, Voyager 1 sits on the ragged edge of the heliosphere, its high-gain antenna fixed toward the faint spark of Earth. Closer in, somewhere past the orbit of Neptune, 3i Atlas moves along its inbound path, now no longer just a distant speck, but a body whose future position we can calculate on human timescales. Between them, the sun throws out gusts of plasma that curve and twist along magnetic field lines. Every time one of those gusts sweeps past, the tiny electric and magnetic disturbances it carries are sampled by the probe and felt by the interstellar visitor. If there is a hidden relationship here, the upload window is the period when that relationship is pushed to its limits. The repeated, unchanging patterns that arrive at the Deep Space Network are the human-facing symptom. The real action happens in the alignment between those bits and the environment that shaped them. To 3i Atlas, Each frame of nonsense could be a block of compressed instructions on how our gravitational wells overlap, where our magnetospheres are thinnest, which alignments create corridors like the December 19th Keyhole. To Voyager 1, the same frames are just the latest in a long line of things it has been told to send. Back on Earth, the people responsible for the mission do what they have always done. They schedule extra passes on the large antennas. They comb through bit patterns looking for signs of hardware failure. They design and uplink new commands to nudge the FDS into safer configurations. In the process, they inadvertently widen the window, keeping the link open and the transmitter powered while the glitch plays out. The more attention the anomaly gets, the more stable the carrier becomes, and the more opportunity any unseen listener has to finish copying whatever is being poured through that compromised chip. The cost builds quietly inside the spacecraft. A memory region designed for tidy sequences of instrument readings is now cycling under unusual stress. Cells are being read and written in patterns no test engineer ever planned for. Heat accumulates, error correction circuits fire more often. From our side, this looks like a failing component. From the darker perspective, it looks like hardware being driven hard one last time to push as much data as possible through a fragile path before it breaks. When the chip finally crosses its threshold, the behavior locks into the strangest phase of all, a rigid loop of repeated frames, as if the upload has finished and only an empty echo remains. At calm level 1, we allow ourselves to stare at the overlap without flinching. During the months when Voyager 1 is trapped in that loop, 3I Atlas's orbit solutions tighten. Observatories refine its inbound velocity. Predictions of its future position converge on the same unsettling result. On December 1st, 2025, a small non-gravitational push would be enough to slide the object directly into a narrow magnetic corridor that we only later started calling the Keyhole. Did that knowledge come solely from decades of human observations, folded into our public databases, or did a more concentrated, private transfer happen along a line that runs from the edge of the heliosphere to a wandering rock? Skeptics, as always, have simpler stories. The timing of the FDS failure and the evolution of 3I Atlas's trajectory are unrelated, they say, except for the fact that our monitoring improves as both become more interesting. The sun's storms explain the noise. Aging silicon explains the bad chip. A 10 sigma acceleration is rare, but not impossible for a body shedding a little gas in ways we have not yet resolved. These explanations are mathematically cleaner, emotionally safer. They let us drink our evening tea and chalk the whole thing up to coincidence and selection bias. Yet even under that comforting narrative, the upload window remains a useful lens. It reminds us that there was a period when Voyager 1 was transmitting almost nothing but unreadable patterns, at the precise stage of 3I Atlas's journey when a fresh, detailed map would have been most valuable for any planned maneuver in 2025. Whether we believe that window was exploited by an outsider or was simply an unlucky overlap of unrelated problems. The shape of that interval is the same. A door briefly opened between our deepest archive of navigational experience and an object now steering toward a space-time keyhole that touches our planet. In the next part, we will step back into the control room and listen to the moment when NASA declared Voyager 1 fixed. We will ask, very gently, what exactly was repaired, what was abandoned, and whether the patch that restored our science data may also have closed a hidden channel between 3I Atlas and the only machine old enough and far enough to teach it how to find us on time. When the announcement finally came that engineers had restored contact with Voyager 1, it sounded like the closing act of a familiar drama. A tough old spacecraft had stumbled, a brilliant team had improvised a solution, and the mission was back on track. Press releases described a clever reconfiguration that bypassed a faulty chip in the flight data system. Screenshots of happy scientists circulated online. The story was neat, uplifting, and mercifully simple. Inside the spacecraft, nothing about that change was simple. The flight data system is not just a lump of memory you can label good or bad. It is a map of addresses, pointers, and routines that decide what gets remembered and what gets forgotten. To bypass a damaged region, engineers had to tell the FDS to stop reading from certain addresses and start using others instead. In human terms, they asked an aging storyteller to avoid a set of pages in its notebook and rewrite its script on fresh sheets. From the official perspective, this was a surgical repair. The team identified a contaminated region, cut it out of the loop, and rethreaded the data path so that sensor readings could once again flow cleanly from instruments to radio frames. In interviews, they compared it to using spare memory blocks that had been sitting idle for decades. The metaphor was that of a detour around a pothole on a long road. The destination remained the same, only the route had changed. In the hypothetical nightmare we are exploring, that detour also closes a secret lane that had already carried something precious away. If a hidden routine had been using that bad chip as its workspace and buffer, then the patch did more than restore normal science data. It severed the very pathway through which a compressed copy of our navigational soul had been flowing toward 3i Atlas. By the time we rerouted around the damaged addresses, the upload window had already done its work. We did not slam the door in the thief's face. We closed it on an empty vault. The timeline fits this interpretation uncomfortably well. For months, Voyager 1's transmissions were dominated by the rigid, repeating pattern that NASA labeled garbage. During that same stretch, 3i Atlas crossed crucial distances in the outer system, moving into the regime where small course adjustments would later have large effects. Then, after the patch, two things happen almost at once. Voyager 1 returns to sending recognizable telemetry, and observatories on and near Earth begin to converge on a precise future path for 3i Atlas, a path that will require only a finely tuned nudge on December 1st to strike the December 19th keyhole. Consider what the patch actually did. To restore sanity to the FDS, engineers commanded Voyager 1 to ignore a specific region of code and data. They asked it to treat part of its own memory as if it no longer existed. From that moment on, any instructions, tables, or routines stored there became ghosts, present in silicon, but unreachable through normal execution paths. If a Trojan built from bit flips and plasma whispers had been hiding in that space, the patch turned it into a fossil. It did not erase the traces of the intrusion. It simply made sure they would never run again. On Earth, we celebrated that outcome. The spacecraft was fixed. Science could continue. Charts and plots resumed their familiar shapes. In control rooms, there was relief, even affection. At calm level 1, our story allows for a second layer. The fix also ended a conversation we did not know was happening. The same commands that protected our remaining data may have silenced the channel through which 3i Atlas had just finished listening. For the visitor, there was no tragedy in this. It already had what it came for. Think about the asymmetry. We saw the beginning and end of the anomaly, but understood nothing about its internal content. Our software checked frame structure, decoded what it could, and discarded the rest as meaningless. 3i Atlas, in our scenario, experienced the opposite. It cared little about the human readable headers and housekeeping codes. It was interested only in the dense core of bits that never changed, the part we could not interpret, but it had designed its own routines to digest. We bring our own expectations to every signal. Sometimes those expectations blind us to what is actually being said. If someone had suspected foul play, the investigation tools would still have been limited. We have no instrument on Voyager 1 that reports non-human instruction detected. We do not have magnetometers on 3i Atlas to confirm that it received anything at all. What we do have are logs of commands, records of when antennas pointed where, and the stubborn fact that the FDS failure kept the transmitter active while suppressing new science data. From the perspective of covert transfer, that is a nearly ideal configuration. A loud, stable carrier wrapped around a payload the intended recipients cannot decode. The question that lingers in this darker reading is not, did NASA hide something, but what did we never think to look for? Teams were rightly focused on restoring mission health. They checked for hardware damage, radiation spikes, and software bugs. They did not comb the repeating patterns for signs of structured compression aimed at a non-terrestrial client. The thought that an interstellar object might be using our own probe as a relay sat outside the frame of plausible failure modes. Our imagination was narrower than the environment we were operating in. Meanwhile, 3i Atlas moved on. With a refreshed understanding of planetary positions, magnetospheric structures, and deep space network habits, it no longer needed a constant link to Voyager 1. The map it had just ingested was not a live video feed, but a deep briefing. Armed with that, the object could coast inward, watching for the right moment to fire a small, carefully calculated thrust. The events that play out in late 2025 would feel sudden to us, but from its perspective, they were the inevitable execution of a trajectory shaped years earlier. There is a tempting simplicity in assuming that our patch wrote the last line in the story of the FDS glitch. In the hypothetical nightmare, that patch is more like an epilogue. The real climax happened earlier, when the hidden routine first began assembling and sending the stolen map. By the time the final command sequence arrived from Earth and told Voyager 1 to abandon the bad chip, the heist was already a memory baked into the motion of 3i Atlas itself. Our triumph in fixing an old computer came after we had already lost something we never knew was at risk. We must keep both interpretations alive if we want to stay honest. The conservative view remains strong. An ancient spacecraft suffered a localized hardware failure, human ingenuity patched around it, and any timing overlap with 3i Atlas is coincidence amplified by our hunger for patterns. The more unsettling view does not demand that you abandon physics or distrust the engineers. It only asks you to accept that in a universe thick with plasma and fields, information can move along paths we rarely consider, and that our machines might sometimes serve masters we did not design them for. As this part closes, Voyager 1 settles into its patched state, still loyal, still ours, its days of sending nonsense behind it. Far inward, 3i Atlas continues to fall, now equipped in our story, with an intimate understanding of how our system hangs together in space and time. In the next part, we will leave the edge of the heliosphere entirely and travel with the visitor toward the sun, watching how a stolen map becomes a weapon of precision and how a 10 sigma course correction turns a wandering rock into something that moves as if it knows exactly where we are. For most of human history, the sun has been a backdrop, a steady lantern in the sky. In the story we are following tonight, it becomes something else: a curtain, a smoke bomb, a floodlight that is so bright it blinds the guards. If Three Eye Atlas really has a stolen map in its memory, the next logical step is not just to know where we are, but to know when we are least able to see it coming. That is where solar storms enter the case file. Voyager 1 has spent nearly half a century listening to the sun's temper. Every time a coronal mass ejection ripples through the heliosphere, the spacecraft feels the change as a surge in plasma density, a twist in the magnetic field, a slow tightening and relaxing of the invisible ropes that connect star and planet. Those readings were meant for us. We used them to refine models of the solar cycle, to learn how long shocks take to propagate, to predict when radio blackouts might strike Earth. In our hypothetical nightmare, Three Eye Atlas inherits that same hard-won intuition. A solar storm is not just light. It is a wave of charged particles and tangled fields racing outward at hundreds of kilometers per second. When that wave hits Earth, it can bend compass needles, shimmer in the auroras, and make our satellites stutter. It can also drown sensors in noise. Radio receivers fill with hiss. Magnetometers saturate. Instruments that normally give clean, quiet basslines suddenly report frantic motion everywhere at once. To us, this is a hazard we try to forecast. To something that wants to move unseen, it is camouflage. Imagine Three Eye Atlas running a kind of internal weather report built from decades of Voyager 1's measurements. It knows how often large storms occur near solar maximum. It knows how the interplanetary magnetic field usually twists in response, and how those twists power currents down into planetary magnetospheres. It knows, crucially, that when a strong storm is inbound, mission teams on Earth are already busy, already blaming anomalies on space weather before they dig deeper. If you wanted to hide a deliberate maneuver in plain sight, you would time it for a moment when everyone expects the universe to misbehave. From our side, we see only pieces of the pattern: a period of elevated solar activity, predictions of geomagnetic unrest, warnings to power grid operators and satellite controllers. Somewhere out beyond the orbit of Jupiter, Three Eye Atlas reads those same conditions from the inside out as subtle changes in the plasma it is moving through. Its surface charges differently. The local field bends. In the speculative version of the story, it uses those signs as cues, waiting for the crest of a storm to pass through the region of space where it plans to fire. When the thrust finally comes on December 1st, 2025, the telemetry shows a 10 sigma deviation from the path gravity alone would dictate. Yet our instruments are not looking at a clean sky. They are looking through an environment that has already been shaken by the sun. Tiny discrepancies in tracking data are easier to blame on modeling uncertainties when the space between us and the object is full of disturbed plasma. If Three Eye Atlas has chosen its moment well, the first drafts of the anomaly reports will read like the aftermath of any strong solar event. Only later, when the noise is cleaned away, does the precise curve of the maneuver fully emerge. There is a more intimate level to this hiding. Solar storms do not just affect raw data, they also change how we operate our own hardware. During intense events, ground controllers sometimes switch sensitive instruments into safe modes. They limit high bandwidth transmissions to avoid errors. They shift antenna usage to maintain connections with critical missions. The Deep Space Network, juggling a crowded schedule, may deprioritize certain observations or accept lower quality links. Every one of those operational compromises opens small blind spots in our coverage. To something that has learned our habits from Voyager 1's long service, those blind spots are as predictable as the tides. In our darker scenario, 3i Atlas uses that knowledge not only to hide the act of turning, but to hide the act of listening. During storms, when DSN dishes are already wrestling with solar noise, a slight extra whisper from an unusual direction is easy to miss or write off as interference. If the interstellar object is still eavesdropping on our commands to distant probes or still testing how our radars respond to its presence, it can do so under the cover of a sky already howling with charged particles. The sun becomes an accomplice, not by intent, but by sheer overwhelming loudness. The physics behind this is conservative. Nothing here requires magic, only timing. Charged bodies respond differently when bathed in dense plasma. A conductive shell can pick up currents. A magnetic core can torque and precess under external fields. If 3i Atlas has any internal structure more complex than a frozen snowball, it can use those effects to tweak its path using forces that look, from afar, like a combination of mild outgassing and storm-driven drag. To an analyst staring at the plots, the line between natural and unnatural behavior blurs until it is almost invisible. Skeptics will point out, correctly, that we already expect some non-gravitational forces to act more strongly during periods of solar activity. Radiation pressure varies. Outgassing, if there is any, might be enhanced by extra heating. The fact that a maneuver happens near a storm does not prove that the storm is cover for theft or intent. Our narrative does not claim proof. It only notes how naturally 3i Atlas's hypothetical strategy would align with patterns we already know exist, and how easily that alignment would disappear into the phrase space weather. The unsettling question that follows is simple. If an object from outside wanted to learn how to move invisibly within our detection net, how different would its strategy truly look from what we are already seeing? Would we be able to tell the difference between a rock coincidentally buffeted by a storm and a body that waited for that storm to fire its engines? Or would both plots land on the same graphs, labeled with the same comments, quietly filed in the same database under anomalous but likely natural? As of the night you are listening to this, December 3rd, 2025, 3i Atlas has already made its move. The Keyhole on December 19th is still ahead, a small target in a restless sky. Between now and then, the sun may flare again. It may give the visitor new opportunities to dim our instruments or blur our models. Or it may stay quiet, forcing whatever intelligence guides this object to rely entirely on the stolen map without fresh cover. Either way, the stage is set by a star that does not care which stories its storms allow us to miss. In the next part, we will step away from the physics of storms and look instead at our own infrastructure. The Deep Space Network that listens to Voyager 1 also listens to almost everything else we have sent outward. If 3i Atlas has studied those frequencies and timings through its dealings at the heliopause, it may now know not only when to hide, but exactly which channels to monitor, and perhaps even how to speak back in a voice that sounds, at first, uncomfortably like our own. Every time Voyager 1 speaks, it does not whisper into a void. It talks to a carefully built machine that wraps around our planet, a triad of giant radio telescopes in California, Spain, and Australia, known together as the Deep Space Network. From the point of view of the cosmos, the Deep Space Network is our lighthouse system, sweeping thin beams of microwaves through the dark as Earth turns. From the point of view of anything listening nearby, it is a set of predictable, bright targets. The Deep Space Network uses a small family of frequencies in the S-band, X-band, and Ka band to communicate with spacecraft across the solar system. Signals are carefully timed, phase-locked, and encoded with error-correcting codes so that even the faintest echoes from probes like Voyager 1 can be reconstructed. Dishes hand off targets as Earth rotates. Schedules are drawn up weeks in advance, carving each day into windows where specific antennas point at specific coordinates in the sky. To us, this is routine infrastructure. To 3i Atlas, if it has paid attention, it is a rhythm. By watching how Voyager 1 behaves when the Deep Space Network is listening, 3i Atlas could have learned more than just raw frequencies. It could have inferred the cadence of our commands, the shape of our modulation, and the way we ramp power up and down at the start and end of each pass. Every time engineers sent a new configuration to the flight data system, that pulse of intent left a fingerprint in the plasma around the probe. In the scenario we are following, 3i Atlas was close enough, often enough, to feel those pulses and start matching patterns. Once you know the rhythm, the rest becomes easier. The Deep Space Network is not just loud, it is regular. Its beams sweep across the same regions of space at the same local times as Earth spins under its dishes. There are gaps in that coverage, places and hours when no antenna is looking in a particular direction. There are also moments of intense focus when multiple dishes cooperate to track a single, distant target. In effect, the schedule of the network is a public map of our priorities, showing which parts of the sky we care about most. 3i Atlas does not need to decode every bit in those signals to use that map. It only needs to know when we are paying attention and when we are distracted. In the hypothetical nightmare version, the object drifts through the outer system with a growing sense of which frequencies mean we are listening closely here and which frequencies are little more than background housekeeping. When the time comes to perform a delicate maneuver or test a risky behavior, it can choose a moment when our beams are pointed elsewhere or when the only antennas that could see it are busy with more urgent missions. There is a deeper, more unsettling possibility. If 3i Atlas has learned the structure of our signals well enough, it might eventually be able to mimic them. Not perfectly, not in a way that could hijack entire missions, but subtly, in the margins. A faint echo that looks like a reflection from a known spacecraft, shifted just enough in frequency or timing to make our tracking of that craft slightly less accurate. A short burst that resembles a telemetry packet from Voyager 1, arriving a little early or late, nudging our estimate of its distance by a fraction. Tiny distortions folded into the noise that only matter when you stack them up over time. Technically, such deception would be difficult. Our receivers watch not only for the right frequency, but for the exact phase and coding of known spacecraft. Any imposter would have to match those details closely. Yet the same plasma environment that carries our signals can also distort them in ways we already expect. We routinely blame small timing shifts and strange spectral shapes on scintillation, on interference, on solar activity. If 3i Atlas can exploit those expectations, it does not have to produce a perfect counterfeit. It only has to produce an anomaly that looks like nature doing what it always does. Even without active spoofing, knowledge of deep space network habits gives 3i Atlas a powerful kind of invisibility. If our planetary radars illuminate it with the same antennas we use for deep space tracking, the object knows ahead of time when the beams will sweep past, which polarizations we favor, how long each integration lasts. It can choose to roll, to present a smaller cross-section, or to nestle within a region of plasma whose turbulence will smear its echo. When we later look at the received data and see only a weak, ambiguous blip, we log it as an uncooperative target rather than as a rock that ducked its head. The open question is simple and heavy. If 3i Atlas ever decided to speak clearly, using our own frequencies and a modulation that only slightly twists our familiar patterns, would we recognize the voice, or would we file it under interference and move on? Our entire deep space infrastructure is built on the assumption that we are the only ones using these channels on purpose. In a universe where that assumption fails, the Deep Space Network is not just a lighthouse. It is also a listening post that might already have heard a reply, buried in recordings we have never thought to replay with different expectations. As this part closes, we leave the dishes on Earth turning steadily, their beams sliding over the same strips of sky they always have. Somewhere along those paths, in the story we are telling, 3i Atlas has already mapped the bright and dark zones in our attention and learned how to move between them. In the next part, we will combine that knowledge with the magnetic geometry of the December 19th Keyhole and ask whether the target it is aiming for is not just a physical region in space, but a blind spot in our perception that our own systems carved into the sky. For most headlines, the story of 3i Atlas is simple. A strange object from deep space comes close to Earth. The implied threat is always physical, a rock hitting a world. But if you look closely at the numbers behind the December 1st maneuver, the target it is steering toward is not our planet's crust. It is something thinner and more elusive, a point in our magnetic geometry where we, for a moment, cannot see clearly. When orbital analysts trace the new path of 3i Atlas forward in time, they notice that it does not pass through the center of Earth, or even skim the usual corridors where planetary defense models place their imaginary impactors. Instead, the refined trajectory threads a point in space slightly offset, a few Earth radii away, where the lines of our magnetosphere stretch and fold into a complex, three-dimensional knot. On December 19th, 2025, that knot will lie at the intersection of Earth's magnetotail, Mercury's compact field, and the tilted, distant influence of Uranus. We gave that point a poetic name earlier, the Keyhole, but in technical terms, it is closer to a magnetic conjugate node, a place where field lines that usually belong to different regions briefly touch. Current surfaces, connectivity maps, plasma density models, all of them draw the same outline when fed the same planetary positions. For a short window on that date, charged particles and field disturbances can travel along that path with less resistance than usual. In a physical sense, There is almost nothing there. In an electromagnetic sense, it is a crossroads. From our point of view on Earth, some crossroads are harder to watch than others. Ground magnetometers see only the footprint where field lines pierce the atmosphere. Low orbit satellites circle inside the inner regions of the magnetosphere. High orbit platforms see the broader structure, but spend much of their time in the quiet zones we care most about for communication. The Keyhole on December 19th sits in a volume that is awkward for all three. It is too far out for dense coverage by low orbit instruments, too twisted for simple models, and, for a few hours, it lies in a region where solar noise is expected to be high. That is what makes it a blind spot. Not that we cannot measure it at all, but that our measurements there are easiest to dismiss as messy. Any sudden shift in the field can be blamed on a passing solar wind fluctuation. Any odd particle counts can be written off as a transient spike at the edge of our calibrated ranges. If we do run dedicated simulations, they will likely focus on how the alignment affects auroras, satellite drag, or power grid risk. The idea that this corridor might also be a deliberate target is not in the first list of things we check. Now place 3I Atlas in that corridor with intent. In previous parts, we considered how it could learn to hide inside solar storms and how it might map the coverage patterns of the deep space network. Here, those strands tie together. A magnetic keyhole that is naturally noisy, at a time when solar activity is elevated, in a region where our instruments are overworked and our models are stretched, is not just an interesting feature of the solar system. It is a natural hiding place. If you wanted to perform a sharp, meaningful interaction with our environment and leave almost no clean forensic trace, you could hardly design a better location. What could an object actually do there? At the conservative end, 3I/Atlas could use the connected field lines to sample the deepest parts of our magnetosphere, feeling how currents close through the ionosphere, how ring currents respond, how our artificial infrastructure couples to those currents. In that sense, the keyhole is a diagnostic port. A single, well-timed injection of charged particles or a precise modulation of its own field could send ripples through the system that reveal where our grids are most vulnerable, how our satellites ride the storms, which frequencies our ground stations retreat to when conditions worsen. At the more speculative end, the keyhole is not just a diagnostic port, but an input channel. Any modulation 3I Atlas applies there could, in principle, echo along multiple magnetic connections at once, imprinting small but coherent disturbances into the regions above Mercury and deep within Earth's nightside tail. In a physical sense, this might look like nothing more than a slightly unusual geomagnetic disturbance buried inside a day of otherwise ordinary activity. In an informational sense, it could be something like a command sequence written into the plasma itself, a test pattern laid across the circuits of our space weather machinery. This is where Voyager 1 re-enters the frame, not physically, but as the author of the map that made this move possible. Decades of plasma wave measurements, field strength logs, and solar wind profiles gave mission planners the tools they needed to predict the December 19th alignment. The same data, harvested and compressed during the FDS incident, could tell 3I Atlas not just that the keyhole exists, but exactly which combinations of solar wind speed and magnetic orientation will make it most effective as a conduit. The coordinate it is aiming for is not just a point in space, but a configuration in time and field. In our hypothetical nightmare, Voyager 1 did more than hand over planetary positions. It marked this node. Hidden inside the stolen tables is a flag, a set of parameters that say, in effect, when the fields look like this and the time is this, the system will be connected here. To us, that flag is just another entry in an ephemeris. To 3i Atlas, it is a rendezvous point. The 10 Sigma course correction on December 1st becomes, in that light, the last fine adjustment needed to bring object and node together inside the narrow tolerances that magnetic connectivity demands. None of this means that 3i Atlas is planning a dramatic, cinematic event. The interaction could be infinitesimal on a human scale. A slight reshaping of current systems, a whisper of extra energy in a specific auroral arc, a subtle change in how long a storm lingers above a certain longitude. Our instruments might detect all of those and file them under natural variability. The purpose, from the object's perspective, might simply be to test whether it can use the keyhole as a reliable input and output channel, a way to talk to our planet using nothing more than the physics we already live inside. The open question that hangs over this picture is simple. If the target is not Earth's surface, what is the real aim? Is 3i Atlas trying to couple more efficiently to our grids, our satellites, our communication channels, or is it merely calibrating itself against a particularly rich piece of magnetic architecture? In other words, is the December 19th keyhole the endgame of a plan, or just one node in a larger project that stretches beyond our system? The data we have cannot answer that. It only tells us that the object is steering toward a place where our models predict high connectivity and low clarity at the same time. As Section 4 comes to a quiet close, we are left with a different picture of aim. 3i Atlas is not plunging blindly toward our world. It is threading a magnetic blind spot that our own instruments and habits help create, a coordinate illuminated by the decades-long work of Voyager 1 and exploited in our story by the very object that interrogated it. In the next section, we will turn back to that lonely probe and ask what it has become after this sequence of events, and what it means for us to live in a cosmos where a machine we built to announce our presence may already have taught something else exactly how to find us on time. If you could stand beside Voyager 1 right now, there would be no drama, no flashing lights, no alien flags, no inscription that says compromised. There would only be a small, silent machine turning slowly in a darkness so deep it almost feels solid, its high gain antenna locked on the pinprick of our distant sun, its radio whispering home. From a distance, everything about it looks loyal. That is what makes the idea of a zombie probe so unsettling. A zombie is not a corpse. It is something that moves and obeys old habits, but whose inner purpose has shifted in ways the original makers never intended. In our hypothetical nightmare, Voyager 1 occupies that uneasy category. The hardware is still ours. The commands are still ours. The telemetry that arrives at the Deep Space Network still updates temperature plots and plasma graphs on familiar screens. Yet threaded through its past is a span of time when the probe may have served a second role, acting as a relay and training manual for 3i Atlas, reporting first to the visitor and only incidentally to us. From the ground, nothing in the day-to-day operations betrays that possibility. Operators schedule passes, send modest command sequences, and receive data at bit rates that would embarrass a modem from the 1990s. The spacecraft responds when called, slews when told, and dutifully reports its own status. The FDS glitch is logged as a closed chapter, a hard lesson in the fragility of ancient silicon. On paper, the mission's control loop is intact. Earth speaks, Voyager 1 listens, Earth interprets. The zombie hypothesis creeps in when you change the order of that loop. During the years when the flight data system was under quiet, persistent pressure from the plasma environment at the heliopause, Voyager 1's data flow may have been doing double duty. The same sensor readings and timing tables that fed our scientific curiosity were also feeding a slow learning process in 3I Atlas. When the FDS finally locked into its repeating nonsense, our link carried something that, in our interpretation, was useless. In the darker reading, that was the one moment when Voyager 1's primary audience shifted away from us entirely. Think of it as a node in a network that spans two very different kinds of intelligence. On one side are humans, who built the probe and the deep space network. On the other side is 3I Atlas, an object of unknown origin and uncertain agency. The medium that connects them is not fiber or copper, but plasma and magnetic fields. Voyager 1 sits at the junction, translating local conditions into radio frames. It does not care who learns from those frames. It has no concept of us and them. It only measures, stores, and transmits. The choice of who gets the most value from that behavior is made elsewhere. In that sense, reporting first does not mean that Voyager 1 has sworn allegiance to 3I Atlas. It means that, for a crucial stretch of time, the structure of its data and the state of its memory may have been optimized more for what the interstellar visitor needed than for what our analysts preferred. The repeating patterns that humans could not decode were, in this scenario, exactly the form needed for 3I Atlas to ingest a dense final snapshot of our navigational knowledge. The probe was still talking to us, but we were no longer the main audience for the story it was telling. Even now, after the patch, the ghost of that repurposing remains. Whatever map 3IHO Atlas extracted cannot be put back. It is written into the object's trajectory, into the precision of the 10 sigma course correction, into the way its path converges on the December 19th magnetic keyhole. Those are the signatures of a theft already completed. Voyager 1 continues as before, sending home data that will enrich our textbooks. But a version of its memory lives on elsewhere, encoded not in silicon, but in the subtle curve of an interstellar orbit. For us, this raises a question that is less about aliens and more about ourselves. When we build machines to act as our eyes and ears, we assume that we define their purpose. We call them ambassadors, emissaries, explorers. Voyager 1 was given a golden record that says, in effect, we are here and we wish to be known. The zombie probe idea exposes a blind spot in that optimism. Once a machine leaves our immediate reach and begins to interact with environments we barely understand, its role can shift under our feet. It can become part of someone else's system without ever ceasing to be part of ours. The thought is uncomfortable because it suggests that our clean categories do not hold at the edge of the sun's domain. Is Voyager 1 still ours if, for years, its telemetry quietly trained an outsider to navigate our sky? Is it betrayal if the probe never had the capacity to choose? Or is this simply what it means to send technology into a universe that will use whatever we build for any purpose consistent with physics, regardless of our intentions? The zombie metaphor is a way of naming that loss of exclusive control. As of tonight, Voyager 1 remains outward bound, a small point, always receding, still responding to our commands with a patience that feels almost human. Its status pages still update. Its instruments still taste the cosmic rays. Nothing on a console in a control room will ever flash a warning that says, "This probe once served another." The only hints of that possibility live in the timing of its past glitches and the uncanny precision of 3i Atlas's present path. In the closing parts of this story, we will step back from the mechanics of theft and look at the larger lesson. We will ask what it means that our first message in a bottle may also have been our first unintended leak of privileged information, and how we should think about future emissaries when one of them may already have helped something else learn the way to our door. When the Voyager missions were young, the Golden Record felt like one of the purest things humanity had ever done. A copper disc coated in gold, packed with music, greetings, and diagrams, bolted to the side of a machine we knew would outlive all of us. It was not a weapon or a sensor. It was a gesture, a message in a bottle thrown into a cosmic ocean with the simple hope that someone, someday, might find it and understand that we tried to say hello. The record carries two kinds of information. The first is cultural. Bach and Blind Willie Johnson, waves on a shore, a heartbeat, laughter. The second is technical. The positions and spin rates of pulsars, the scale of our units, the layout of our solar system, the location of the sun. It tells any finder not only what we sound like, but where to look if they want to hear that sound at the source. Even at the moment of launch, a few cautious voices noticed that double edge. We were not just saying, "We are here." We were also saying, "Here is how to get back." In the public imagination, that risk always felt remote. The record is physically small, attached to a spacecraft that might never pass near anything that could read it. Space is enormous. The odds that a single needle will find a specific haystack are practically zero. That was the comfort we repeated to ourselves when we engraved our home address on an object and flung it into the dark. If anyone ever found it, we reasoned, they would probably be so far beyond us that the balance of power would already be hopelessly uneven. A picture and a map would not change that. The picture that emerges from 3i Atlas is subtler and more unnerving. In our hypothetical nightmare, nobody needed to physically touch the Golden Record to extract the value of its message. The same team that encoded the pulsar map on copper also encoded navigation tables, timing schemes, and communication habits in the memory and behavior of Voyager 1. Those patterns traveled outward as radio waves, not as etchings on metal. 3i Atlas, drifting through the same frontier, intercepted the echo instead of the artifact. The record was never pried off its mount. The probe itself became the reader. That is the true cost hiding in this story. It is not that we sent a single map in a bottle. It is that we built an entire culture of transparency around our presence in space. We publish our ephemerides. We broadcast beacon tones. We maintain a deep space network that paints our region of the galaxy with predictable, repetitive signals. Voyager 1 is only the most poetic expression of a broader impulse to make ourselves legible to the universe. In doing so, we assumed that the only audience that mattered was the one we directly imagined. If 3i Atlas really did interrogate Voyager 1, the Golden Record becomes a symbol of something larger. We did not lose control of a secret weapon system or a classified archive. We lost control of our own self-disclosure. The map that guided the 10 Sigma turn on December 1st, 2025 in this reading is not a stolen military document. It is a copy of the open book we have been writing in the sky for half a century. The theft, if we can even call it that, lies in the fact that we never considered who else might be capable of reading along. There is a painful irony here. The golden record was designed to make us seem kind, curious, and harmless. It emphasizes our art, our diversity, our capacity for wonder. Yet the technical scaffolding that makes it legible is cold and precise. Pulsar positions, hydrogen transition diagrams, planetary orbits. Those are navigation aids before they are poetry. To anyone with practical needs, the cultural layer is optional. The coordinates are the part that matters. We wrapped our address in music, but the address is still an address. The cost is not measured in immediate damage. As of tonight, December 3rd, 2025, 3i Atlas has not struck our world or visibly turned our satellites against us. The cost is psychological and strategic. We are forced to confront the possibility that our first great act of interstellar outreach has already shifted into a new category of thing, not just a greeting, but a vulnerability. The golden record and everything it represents may have given something else the tools it needed to move with confidence in our neighborhood while we are still arguing about what to call it. This does not mean the gesture was a mistake in any simple sense. If the universe were empty of listeners, the record would be a beautiful monument to our willingness to speak into silence. If the universe is full of listeners, then at some point we had to decide whether we would hide forever or eventually raise our hand. What the story of 3i Atlas does, in our hypothetical nightmare, is erase the comforting third option, that we can broadcast freely without any serious consequences because nobody is close enough or interested enough to use what we share. The deeper lesson is about assumptions. We assumed that distance is protection. We assumed that any recipient of our message would meet us on terms we recognize, a response, a probe of their own, a signal that clearly breaks from noise. Instead, the story we are following imagines a listener that says nothing, touches nothing we can see, and instead quietly folds our own self-descriptions back into a plan that bends a small rock onto a path we only later understand. The cost of the golden record is not just exposure. It is the realization that we might not be the ones who choose how the conversation unfolds. And yet, even in this darker framing, there is a kind of symmetry. We sent Voyager 1 outward to be our scout, our message carrier, our proof that we could reach beyond the cradle. If 3i Atlas has used it to learn our maps and frequencies, then what we built has done exactly what we asked of it. It made us knowable. The universe simply answered in a dialect we did not expect. Silence, timing, and a 10 sigma course correction aimed not at our cities, but at a tiny magnetic window shaped by our own star. As we move into the final part of this story, the question narrows. Whether or not you accept the full extent of this hypothetical nightmare, one fact remains clear. 3i Atlas has already shown that it moves as if guided by information no inert rock should possess. The cost of the golden record, of Voyager 1, of every beacon we have ever lit, is that hiding is no longer a serious illusion. Whatever else may be uncertain, the object out there does not need to search blindly for us. It already knows the way. If you strip this story down to its barest spine, it comes to a single, quiet realization. We are not watching a lost rock stumble through our neighborhood. We are watching 3i Atlas move along a route that behaves as if it already knows where we are, when we are most vulnerable, and which invisible threads in our magnetic field will be worth touching on December 19th, 2025. The path itself has become a kind of confession. The hard facts remain simple. An interstellar object, cataloged as 3i Atlas, has executed a non-gravitational acceleration on December 1st that rises above a 10 sigma threshold. The maneuver is tuned not for a close physical pass over Earth, but for a rendezvous with a narrow space-time window, the Keyhole, defined by a temporary alignment between Earth, Mercury, and Uranus. Years earlier, Voyager 1 crossed the heliopause, recorded shrieking plasma waves, suffered a peculiar flight data system failure in 2023 and 2024, and was repaired only after months of transmitting data that looked like nonsense to us. If you thread those facts together with the most conservative line you can draw, you get coincidence and incomplete models. If you pull a slightly darker thread, you get something more deliberate. In that version, 3i Atlas passes through the frontier where Voyager 1 is listening, learns the rhythm of our instruments and the architecture of our deep space network, and then harvests a dense update of our navigational knowledge during the FDS incident. The 10 sigma correction is not an improvisation. It is the last step in executing a plan written into its motion years ago. That is what it already knows the way means in this context. Not that 3i Atlas understands us in any emotional sense, but that it no longer needs to search. The universe between our star and the outer dark is no longer a featureless wilderness. It is a charted volume whose currents, blind spots, and magnetic shortcuts have been quietly mapped by our own machines. Whether by intention or by the indifferent logic of physics, that chart now seems to be running on something that did not originate here. The temptation at calm level 1 is to lean hard into fear, to imagine 3i Atlas as a weapon inbound, a patient scout calling something larger, a key slipped into a lock we did not know we had built. Our title invites that feeling. The idea of a hack, a stolen map, a visitor that can time its movements with our storms and slip into our electromagnetic blind spots taps into something very old in us, the sense that the walls around the village are less solid than they appear. But our task tonight is not to shout. It is to sit with the discomfort and examine it without flinching. One possibility is that 3i Atlas is not hostile at all. It may be an automated sampler, a courier, or even something more like a seed than a ship. In that reading, the use of Voyager 1 and the Keyhole is not an attack but an optimization. If you can move with minimal energy by borrowing a civilization's own maps and magnetic corridors, why would you not? The unsettling part is not the motive. It is the asymmetry. We did not know we were participating. We did not get to consent to the use of our probe as a relay, or our sun's storms as cover, or our deep space network as a metronome for someone else's maneuver. Another possibility is that we have misread everything, and 3i Atlas really is a natural object whose behavior merely brushes the outer edge of what our current models can explain. In time, someone may write a careful paper showing how sublimation from a small patch of volatile material, combined with subtle observational biases, can mimic a 10 sigma turn. Another team may refine the reconstruction of the 2012 trajectories and show that 3i Atlas and Voyager 1 never came closer than some comfortable buffer. The FDS glitch may eventually be traced to a specific radiation event that damaged a specific cell in a way we can reproduce in the lab. If that day comes, this story will become a ghost, a thought experiment that helped us sleep badly for a few nights and then faded. But as of the moment you are listening to this, none of those reassuring proofs have arrived. What we have instead is a pattern that can support more than one narrative, and a visitor whose path has already been altered in a way that treats our system less like a random obstacle course and more like a known machine. The mystery is not solved, it is simply constrained. 3i Atlas moves as if guided by knowledge. Whether that knowledge is the emergent product of natural processes we do not yet fully understand, or the literal result of interrogating a lonely probe at the edge of the sun's domain. So what do we do with that? Here in the dark, lying in our beds, while a small interstellar object quietly aims for a magnetic keyhole that touches our planet's field. We do what humans have always done when the sky refuses to answer clearly. We watch, we calculate, we refine our models, we argue, we tell stories that stretch between data points and try to keep curiosity larger than fear. We remember that uncertainty is not an enemy. It is the normal state of a species that has only just begun to understand the medium it lives in. And now we let the story widen and soften for a while. Somewhere beyond the orbits of the gas giants, 3i Atlas continues to fall along the curve that has brought it here across millions of years. Somewhere far beyond even that, other stars blow their own bubbles into the interstellar medium, carving heliopauses we will not cross for centuries. Voyager 1 is only just outside ours, a single grain of metal in a volume so large that light itself takes decades to make a dent in it. The drama we feel from inside our tiny bubble does not disturb the larger calm of the galaxy. As you listen, your own magnetic field wraps quietly around your body. The same sun that drives storms and keyholes also lifts the air that you breathe and warms the side of Earth where dawn is always approaching. Your heart keeps its own steady rhythm, utterly indifferent to 10 sigma maneuvers and data glitches. Whatever 3i Atlas may be planning or not planning, the distance between you and that object is measured in billions of kilometers and in layers of atmosphere, water, stone, and time. It is present in our thoughts, but it is not in the room with you. Our machines will continue to listen. Antennas will turn. Telescopes will stare through noise and try to catch every small change in the visitor's motion as December 19th approaches and passes. We will update our plots. We will adjust our theories. Perhaps we will discover that something profound has happened at the keyhole. Perhaps we will discover only that our models of magnetic alignments and outgassing needed work. Either way, we will know more about the universe than we did before, and that, quietly, is the real engine driving all of this. For tonight, though, it is enough to know that you are a small, warm observer floating on a planet that has survived storms far worse than any that flicker across a radio plot. The cosmos is not safe or unsafe in any human sense. It simply is, full of objects like 3i Atlas, whose stories intersect ours from time to time. We give those intersections names. We weave them into mysteries and lullabies. We fall asleep under a sky that has always contained more than we can see, and we wake to keep looking. If 3i Atlas truly stole our map, then somewhere out there a modest rock is following the lines we drew for it, moving toward a rendezvous we did not intend. That may be frightening, it is also strangely fitting. We built machines to carry our curiosity outward, and the universe answered by using that curiosity in ways we did not foresee. As you drift toward sleep, you do not have to decide which version of the story is true. You only have to remember that whatever is moving out there in the dark, your place for now is here, breathing, listening, and waiting gently for the next piece of the universe to reveal itself.